Hello everyone, this is CLO 2.3. We are going to derive and validate trigonometric identities and then use those to simplify expressions. Okay, we're going to start off just listing out the different reciprocal identities. Remember, reciprocal identities mean that they are related in a fractional way where you just flip the top and bottom of a fraction. So the cosecant of x is 1 over the sine, or I think before in the previous slides we said sine is 1 over cosecant. Secant is 1 over cosine, or you can say cosine is 1 over secant. Cotangent is 1 over tangent. Tangent is 1 over cotangent. In addition to that, in the previous videos we talked about how tangent of x is y over x, but in addition you can say tangent of x, that was on the unit circle, but we can also just say tangent of x is sine over cosine, and therefore the reciprocal of that cotangent is the cosine over sine. So in the next slides, we'll use these facts to derive different identities. So let's do this first example. It says verify this identity. And when they say verify, what you need to do is just change either the left or the right side of the equation, and until we get to the left and the right being exactly equal. The habit I like to choose is, if we can, to switch everything to be in terms of sine and cosine. So the cotangent of x is actually equivalent to 1 over the tangent, or it's equivalent to the cosine of x over the sine of x. You can go back to that previous slide or go back in the video and see that identity. And when you have sine x on top and sine x on the bottom, those will cancel, and we'll be left with the fact that cosine x equals cosine x, which everyone can agree is true, and therefore this identity is also true. Let's look at another one. We've got cosine x times tan x equals sine x. And again, often my habit is I like to change everything into sines and cosines if possible. So we'll change that tangent x to be the sine x over the cosine x. That's one of the identities. And then again, we have this situation where the cosine on top of a fraction, the cosine on the bottom will cancel, and we are left with the fact that sine x equals sine x, which everyone will agree is true, and therefore the original identity that we were trying to prove is also true. Sometimes instead of just verifying identities, we have application questions where we can use the identities to answer other questions. So in this example, they're asking for the cotangent of x. Well, again, I prefer to move things in terms of sine and cosine. So the cotangent of x is the cosine of x divided by the sine of x. That's one of the quotient identities. And we're given the value of cosine of x, 12 divided by 13. The value of sine of x, 5 divided by 13. This dividing by 13 on both sides cancels, and we'll get in the end that the cotangent of x is 12 over 5. Okay, this second example, we want to find the value of cosecant of x. And if you remember, cosecant of x is the reciprocal identity to sine of x, and they gave us the value of sine of x. So that's 1 over 4/7, which would simplify to be 7 over 4. Okay, there's another set of identities to do with negatives. And just very quickly, I'll explain a little bit. If we remember what the sine graph looks like, it starts at 0, 0 and moves in this wave pattern. So this expression on the left, sine of negative x, they're saying if you input a negative x value, what's the sign going to be? Let's use that one as an example. And it turns out that that will exactly be equivalent to the positive angle on the same side, let's say here, but then you reflect that, you make it negative, you reflect that value down, and you will see they're going to have that same height, that same y value. So anytime you see the expression sine of negative x, you can replace it with negative sine of x. Those are identities. Okay, the next identity has to do with cosine. It's a little bit different. And let's draw the cosine graph that we've discussed before. The cosine graph moves in a wave pattern, but it starts at the highest point and goes like this. And so let's see what the identity is saying. It's saying the cosine of a negative angle, so the output of a negative angle is going to be exactly the same as the output of that equivalent positive angle. And this has to do with the fact that the cosine is a mirror image across the y-axis. So it doesn't matter if you're going to the left or going to the right, you're going to be arriving at the same height. This actually, it's called an even function, but that's what this identity is saying. The cosine of a negative angle will be exactly the same as the cosine of a positive angle. And lastly, the identity for the tangent function. Remember, the tangent function has some places where it's undefined, so it kind of repeats in this pattern. Okay, and so let's look at what they're saying about negative angles and so on. So a negative angle, remember, you're moving to the left of a horizontal, so let's put an angle right there. It says the tan of a negative angle, so the output of tangent when you have a negative angle is related to the output of that same positive angle in the sense that you have to make it negative. This is what we call an odd function, similar to the sine, but that is the identity that we need to remember. The tan of a negative angle is negative the tan of that corresponding positive angle. Okay, so here is a related identity that we can verify. Remember, to verify, we just need to substitute and get the left side of the equation to be exactly equal to the right side of equation. Usually a good strategy is to move everything to be in terms of sines and cosines. So I'll look at the left, and I notice that secant is equivalent to 1 over cosine of negative x. And on the right, secant of x is equivalent to 1 over cosine x. And then I use the negative identity. Because cosine is an even function, it means that the cosine of negative x is exactly equivalent to the cosine of x. So on the left, I have 1 over cosine x. On the right, I have 1 over cosine x. So everyone will agree when we see that this identity is also, it also holds. So in addition to verifying, we can apply and answer questions. So let's look at cosecant of negative x. And we know that the cosecant of negative x, I like to move things in terms of sines and cosines. So this is the sine, 1 over the sine of negative x. And remember, the sine of negative x is an odd function, which means that that's exactly equivalent to negative the sine of x. Well, negative the sine of x, we know what the sine of x is, so it's going to be 1 over negative 1/2. If you want to simplify that, that equals negative 2. So we can say the cosecant of negative x in this particular case equals negative 2. Okay, we'll look at another application, and they only give us the value of sine x, and they want us to figure out the value of this very complicated expression. So don't get scared. We'll just go step by step. And first step, I always like to get it in terms of sines and cosines if possible. And so the cosecant is just 1 over the sine of negative x, the cosecant of negative x. And this is already a cosine, so we'll leave it. The secant is just 1 over the cosine of negative x. All right. And again, we'll use the negative identities. And since sine is an odd function, we can replace it with saying the negative sine of x. And we'll leave cosine x the way it is. And cosine is an even function, which means cosine of negative x is exactly equivalent to the cosine of x. And so we've got negative 1 over the sine x here. Now we've got cosine divided by cosine, just simplifies to be 1. So now we can go ahead and plug in our values. We've got negative 1 over 3/5 plus 1, which ends up being negative 5/3 plus 1, which equals negative 2/3 as our final answer. Okay, there's another set of identities related to sine, cosine, tangent called the Pythagorean identities. So as you will remember from our previous lessons, the Pythagorean theorem says that the leg squared plus the leg squared of a right triangle equals the hypotenuse squared of that triangle. Now we can rearrange things a little bit. If we choose to divide every single term in this equation by the same thing, it doesn't change anything. Remember what you do on the left side of an equation, if you do exactly the same thing on the right side, it doesn't change anything. So if we decided to divide each and every term by c squared, that would be no problem. We're doing the same thing on the left and the right. We could rewrite this as a over c, a over c squared plus b over c squared. C squared over c squared is just 1. Now a over c, just remember, this is a ratio in a right triangle. If we look at, for example, if we look at this angle, theta, a is the opposite side, c is the hypotenuse, b is the adjacent side. So a over c is the opposite over hypotenuse. Another way of saying opposite over hypotenuse is sine. So we have sine theta squared. And then b over c is the adjacent over hypotenuse. That's cosine theta squared equals 1. And one more step just in math. We want to save time without having to write the parentheses. So the way we write sine theta squared is we put the squared right there. We say sine squared theta plus cosine squared theta equals 1. And that's one of our identities. Now there's 2 other identities. This one we derived. We're not going to take the time on this video to derive these 2, but we could. It's similar. Usually you just move everything to sines and cosines and we'd be able to derive each one of these identities. We're not going to take the time to do that, but we will use these. Let's look at this example and see if we can verify this identity. So again, the way you verify anything is you make the left side of the equation look like the right side. Now what I notice is sine squared, cosine squared, and cosine squared. So what I'm first thinking is if there is a way to get rid of the sine squared, then I'm getting closer to have the left and the right look the same and have only cosine squareds. So I'll go up to this identity and rearrange this. This first identity, not only is sine squared plus cosine squared equal to 1, but I could easily rearrange this equation to get exactly just what does sine squared equal. So what I'll do is subtract cosine squared from both sides, and then I get sine squared x equals 1 minus cosine squared x. So I'll replace that here in this example. Instead of writing sine squared, I'll replace it with 1 minus cosine squared x, and then leave the rest of the equation the same. 2 cosine squared x equals 1 plus cosine squared x. And just notice, this is minus 1 cosine squared x plus 2 cosine squared x. So this simplifies, it's like minus 1 apple plus 2 apples. You just get plus 1 cosine squared x equals 1 plus cosine squared x. I think we can see that both sides are exactly the same, and therefore, 1 cosine squared x is 1 cosine squared x, and therefore we have just verified this identity. Okay, I was wrong in what I said before. We are going to verify the 2 other identities, and typically, as the way I like to do it, if we move everything to sines and cosines, it simplifies things a little bit. So tangent squared x, just remember, tan x is equal to sine x over cosine x. So this is going to be sine x over cosine x. And that's all squared because it's tangent squared. So the better way to write it is sine squared x over cosine squared x plus 1 equals secant squared x. Secant is just 1 over the cosine squared of x. Now let's look on just the left-hand side and see what we can do to rearrange things. So we've got sine squared x over cosine squared x plus 1. I would like to get a common denominator and combine this into just one fraction. So I'll multiply both sides. I'll multiply 1 by cosine squared x over cosine squared x. Remember, cosine squared over cosine squared, anything over the same thing is just 1. So it's just like I'm multiplying by 1, which is not changing anything. I'll leave the right-hand side the same. But now on the left, I have a common denominator, so I can say sine squared x plus 1 times cosine squared x is just cosine squared x all over cosine squared x is supposed to equal 1 over cosine squared x. Well, remember the Pythagorean identity that sine squared plus cosine squared equals 1. So on top, we've got 1 over cosine squared x. And that's the left. On the right, we've got 1 over cosine squared x. We made them match, so we verified the identity. Okay, we'll follow a similar process to verify this third trig identity. Let's move everything to be sines over cosines, sines and cosines. So cotangent is the cosine. Let me write this first. Here is what we're trying to verify, that the cotangent squared x plus 1 equals the cosecant squared x. We'll change cotangent squared. The fact that cotangent is cosine over sine, so cotangent squared is cosine squared x over sine squared x plus 1. We want to see that it equals cosecant squared x, which cosecant is just the reciprocal function of sine. So we want to show that it equals 1 over sine squared x. Again, we'll multiply both sides of, top and bottom of this number 1 by sine squared over sine squared, which is just, when you multiply by same over same, it's just like multiplying by 1. It doesn't affect the equivalency. Now we've got a common denominator. Cosine squared x plus sine squared x is what's common on top. The common denominator, sine squared x on the bottom. We want to show that that equals 1 over sine squared x. Well, on the top, that is a trig identity, where we can see cosine squared plus sine squared is the same as sine squared plus cosine squared. All of that is equal to 1. That's the Pythagorean identity. So we've got 1 on top over sine squared on the bottom equals 1 over sine squared, which we can see left and right are the same. We have verified this identity. Okay, let's do an application question where we have this Pythagorean identity and we want to find the value of cosine x. So sine squared x plus cosine squared x equals 1. Let's subtract sine x from both sides, sine squared x on both sides. And we've got the fact that cosine squared x is just 1 minus sine squared x. Okay, well, let's replace what we know. That's just 1 minus, sine of x is 2/3, so 1 minus 2/3 squared. We get that cosine squared x equals 5/9. Now we can take the square root, so cosine of x equals plus or minus the square root of 5/9. So cosine x equals plus or minus the square root of 5/3. Okay, well, sometimes you will see expressions, and the question is this an identity or is it not an identity? And there's some, what that means is that you're going to have an equation, something equals something, both the left and the right will have variables in them. And what it means to be an identity, it means if you plug in any value at all, to that expression, then the left side and the right side will always be equal. So here's an example where we are trying to figure out, is this an identity? And what that means is this always true for any x? So if we plug in some values and it keeps being true, then we can say, okay, it probably is an identity. If we plug in some values and we find even just one value where it's not true, we just say, no way, that's not an identity. So this question is saying, hey, plug in these values and see, is this probably an identity? We'd say yes if they all work. We'd say, yes, it's probably an identity. We'd still have to do some other verification. But if we find even just one of these values where the equivalency doesn't hold, we'll say no. So let's start off with when x equals 0. If we plug in tan of 0 plus 1, we would get a value of 1. If we plug in secant of 0 times cosine 0, I put theta, habit, cosine, I keep saying that, cosine 0 minus sine 0, we end up also getting 1. So far, so good. Let's put in x equals pi to the left side. We'll get tan of pi plus 1 is 1. We'll get secant of pi cosine of pi minus sine pi. And when you plug all that in, you get 1. So far, so good. Let's try x equals pi over 2. And you plug in, well, what's the tan of pi over 2 plus 1? And it ends up being undefined. Don't get scared. If the other side is also undefined, it still matches. So the right-hand side would be secant pi over 2 times cosine pi over 2 minus sine pi over 2. We plug all that in, and we also get undefined. Still looking good. And then now we'll try, as they suggested, try pi over 4. We plug in pi over 4, we get tan pi over 4 plus 1, we get the value 2. On the right-hand side, if we plug in secant pi over 4 times cosine pi over 4 minus sine pi over 4, we actually get a different value. We get 0. So this right here is the problem. We found an example where the left-hand side does not match the right-hand side, so we say not an identity. If you can just find one example of an input value where this equation does not hold, then it's not an identity. Okay, thank you. Hopefully this video helps.